Thank you, Joy. Hello, everybody, and welcome to this session. I'm really glad you could make it. The topic of my talk today is scaling Spark applications by connecting code to resource consumption. This work that we did to support this talk was inspired by our customers who face a common challenge. I have developed a Spark application on my test cluster using a small set of nodes, possibly sample data, and likely nothing else running on the cluster. And now this application is taken to a production cluster, and things don't go quite so smooth. And the customers are left spending a lot of time and energy trying to debug these performance problems. And this is where we come in. Before I go into the talk, maybe a quick minute to describe what Pepperdata does and what we bring to this problem and what gives us credibility to solve it. Pepperdata has been doing performance optimization for big data clusters for the last 5 years. Our resume can be summed up in 3 numbers: 18,000, that's the number of nodes, production nodes, that our software runs on. Our largest clusters tend to be in the multiple thousands of nodes. And on these clusters, we see over 50 million jobs every year. We are analyzing them, we're optimizing them, and so we've stored and collected over 200 trillion performance data points to support this activity. So this gives us a unique perspective and experience in solving this problem. So my talk today will cover 3 sections: why debugging is hard for Spark applications, what are the elements you need to get a complete view of your application's performance in production. Today, this is available through separate tools. I'm going to bring them all in one tool and show you how you can debug your Spark application performance. So why is it hard to debug performance problems? We contend there are 2 reasons. Reason number 1, it shows itself as a common external symptom. The complaint will be, hey, my job's running slow. But you could have many causes for why your job's running slow. It could be the code. It could be the data. Maybe you have too many partitions. Maybe you have too few partitions. Maybe your configurations are problematic. Spark has a wonderful set of configuration parameters, but if you don't know what you're doing, you could land yourself in trouble. The final one is cluster weather. For those of you who are unfamiliar with this term, indulge me in a personal analogy for what cluster weather means. A couple of days ago, I was driving to work, and I was taking my sons to school. My oldest son, Nirvan, his school is about 5 minutes drive under best circumstances. So that's my SLA with him. I'll drop you off in 5 minutes. But that day, my car, we live at the bottom of a hill. As I was going up, there was a dump truck in front of us that slowed us down. We get to the traffic light, there's a big line of cars that's also slowing us down. There's pedestrians on the road, there's other traffic on the road, and so long story short, I ended up blowing my SLA by close to 15 minutes, and my son reached school at about 20 minutes. So how does this apply to your Spark application? Think about your jobs. They get scheduled, and resource manager might take a long time before it puts your job from a queue into running on the cluster. You're contending with a number of other applications that are also using the cluster resources. Think about that dump truck. I'll come back to that in a later example. So all of this external ambient circumstances can slow your application down, and that has no fault of your application, but you don't know that when you look at just the numbers that the application ran through. So that's reason 1. What's reason 2? We contend that the existing tools that are available provide very limited visibility. The analogy that comes to mind is looking for a problem in the dark with a flashlight or looking for it at daylight. So each tool will give you a view into the problem, and then you have to stitch together multiple views to get at what the root cause is. This is not a comprehensive list of tools available. That's not the purpose of this slide. But to kind of give you Spark Web UI, this is, of course, the most popular tool out there. What it does really well is it breaks the application down into its logical plan and its physical plan. And I'll describe this in a little bit more detail later. And it also gives you some aggregate performance data, which when you're trying to winnow down your problem from a large number of applications to just the few problematic ones, aggregate data is good. But when you're trying to dissect a problem in a single application, that's not quite so useful. You have a lot of tools that give you time series information about your cluster, how are things going, but they're not really tied to your Spark application to give you insights into your application. And in general, we think there are two problems with the tool sets that are available today. Your code execution, the code you're executing is not connected to the resource you're consuming. Now, why is that important? Let's say you have a very long application that runs many stages, and there's just one stage that is the resource pig. If you don't know which stage it is, your entire application is the resource pig, and the entire application is what you need to debug. So connecting that is important. We've already talked about cluster weather, and the last point just makes that. It's like, how do you know what other applications and your hardware actually is doing to affect the performance of your application? So those are the reasons. Let's look at the solution. In our experience, there are three elements that form to give you a complete picture of Spark's application performance. We've talked about one, code execution. You need to know what code is being executed when and where. You need a time series view of your resource consumption of your application. Why is this important? We as humans are really good at looking at time series data and kind of pointing out, hey, here's a pattern that's recurring, or here's a big spike. That's very easy for us to understand, and we can understand what outliers there are in the code. Finally, there's cluster weather. We've already talked about it, so I'm not going to spend too much time on it. But any solution needs to have these three elements. So let's look at these in isolation and show you the first half of the solution that gives you the logical and physical execution plan. The example I have here is available freely using the High-Bench Spark test suite. I'm running Scala PageRank application here on a 4-node cluster running Cloudera and Apache and Spark 1.6. So the area that is of interest to me is the one in this green area. So it tells you the logical plan. It gives you the stage ID. It gives you the start time. It also, very importantly, tells you, demarcates the part in your code that triggers off the stage. So this was the wide transformation. That was the end of that stage. So you have a clue as to where to look in your code if you think that a stage has a problem. As you can see on the right, there's a lot of aggregate information that's also available. If you're familiar with the Spark Web UI, this is also very familiar to you. This is the physical execution plan that Spark creates. So you have all your data that's divided into partitions. Each partition is executed on by a task, and the tasks get in turn executed by the executors you have in your that you have specified at startup time. So the physical plan tells you how Spark distributes these executors, and it also gives you some information in aggregate. I want to draw your attention to the area in red. If you look at this, the takeaway might be that, hey, this application is likely doing too much garbage collection. What is going on? Is this a problem with memory constraints on this? Should we increase the memory? And the other question is the garbage collection happening throughout your application, or is it happening just in one section of your application? That information is not available when you look at this view. So let's look at the other side of this solution, which is the time series view. Here I'm charting out 4 resource consumption vectors. We can, of course, have a lot more, but we think these are the most important when you're trying to debug performance problems. CPU across the life cycle of the application, memory, garbage collection, and HDFS reads. Now you see a little more delineation in your garbage collection. There is garbage collection going on, but there's a huge storm of garbage collection activity towards the end of the application. Now you know you can narrow down your search if you knew what stage was executing in that particular time. So let's bring this together and show you what the tool looks like when you bring these together. So here's one resource consumption vector, CPU. This is plotted over the life cycle of the application, and in the area in green, these alternating bars of light and dark blue show you what stage it's being executed in. So starting with stage 0 through stage 5, sorry. At the bottom of the page, you can also see the code section, very similar to what you see in Spark. And we also provide you with kind of the average execution, average CPU that your application has consumed in each stage. So you can see if your average CPU is really high in a particular stage, maybe that stage has a CPU-bound problem. You can layer in memory, and we also provide you with the max memory used. You can layer in GC, and now the question we started to ask is answered. The GC storm happened in stage 4. We'll deep dive into that, and we also provide you with kind of how much time are you spending doing GC in each stage. The last execution parameter, sorry, resource consumption parameter we have is HDFS. And logically, it makes sense that most of the HDFS reads happen in the first stage of the application. One point to note, if you see HDFS reads happening within at the boundary of each stage, that's an indication that you're doing spill, that your shuffle data is spilling over into disk, and maybe you want to look at memory. Here it looks like we're not spilling to disk. So you can bring all of these together, and this is what the tool looks like when you try to, it's kind of your homepage, if you will, of the application when you start looking at it from a performance perspective. So we looked earlier at GC. So let's dive into that particular stage in which we saw the potential GC performance issue. It gets highlighted, and that stage tells you kind of where the code section is, when it started, and kind of different vectors of resource consumption for that. So you can dive into this stage and get a more comprehensive view of that stage and how the executors are doing. Let me orient you to this slide. On this, these blue bars basically represent the work done by each executor in that stage. The green bars are the work done by that stage by tasks. Green would be successful tasks, and red would be failed tasks. So here are the corresponding time series view of each executor, and you can drill down and find out which particular node a particular executor is running on, and this is the resource consumption profile. Now, one thing that sticks out is, yes, there is garbage collection activity happening. Most of it seems to be coming from one executor, and likewise, it's also doing a lot of work, which seems to correspond with the big executors queue we see here, where this is like twice as long as the other executors. We can highlight that particular executor, so you can see that the problem is more likely that while there is GC activity happening, it's because of the amount of work that this executor is doing. In this case, it's doing twice as much activity as the other executors. So a solution which we come up with is more likely around data skew and not around memory constraints. So this basically gives you an overview of how you can get a little more granular detail of a problem when you start out with just looking at a kind of entire view that says GC may be a problem. What if it's not your fault? That would be nice. Let's take a look at this. Here I have another high bench Spark example, Scala Terasort, and I had 3 runs of it on the same day. 2 of them took about 24 minutes, but you have this one here over an hour. Now, what could have happened that caused this application to run that much longer than the other two? If you look at Spark Web UI, there isn't that much detail that you get. It basically gives you the same information, just broken down by stages. The aggregate data is pretty much the same between both runs of the application. So let's flip over and look at the time series view. Now a little more detail comes into picture. This is the fast run and this is the slow run. What you see is in the fast run, you have much higher peaks of resource consumption. Here you see CPU, memory, and HDFS reads. And here, this is really depressed. Each of the peaks are much lower in the slow run of the application. So you know why your application took longer in this run. It was getting fewer resources. But what was stealing those resources away from your application? You can look at the cluster weather view, if you will. That happened when this application was running. This will show you, I'm going to show this to you in 3 separate charts. The first is CPU. What you see here is, that was the big dump truck I was talking about earlier. Here you have one application, and you can see who the user is, what queue it is, what the application is. It is just pounding on the cluster, giving our application, which is the area in green, a very negligible portion of the resource of your cluster. And once it is done, our application is able to chug along with greater CPU consumption. Another view, the memory consumption. Here again, you'll see that while there are other applications that are also consuming memory, the one in area in red is the biggest contributor to memory consumption, and it is stealing resources away from your application. Likewise, for the HDFS, you can see that HDFS read took a much longer time simply because another application was accessing the I/O at the same time and really hogging the resources. So here, hopefully you get a sense of what cluster weather can do to your application and why, instead of chasing your tail trying to figure out what happened to a particular application, you can actually look at what caused it to slow and avoid a lot of time debugging the problem. So to recap, integrating your execution plan with the time series gives you an ability to shine a spotlight kind of on problem areas in your application. Integrating stage and code sections gives developers the ability to say, what is the most impactful area of optimization? So you can look at it and say, I consume the most resources in this section, maybe this is what I need to optimize for. And finally, knowing cluster weather can prevent valuable time wasted debugging non-existent performance issues. So I've been talking about the tool, do a little plug for it. The tool is the code analyzer for Apache Spark. We are offering it for free during early access, which started yesterday. Early access is primarily intended for development teams so that we can get feedback from you guys and refine. I have 2 colleagues of mine waiting in the back. And if you have questions, there's also a little card we have. If you fill it, you'll be in for a drawing, for a gift card. Please visit our booth. It's Pepperdata, booth 101. It's right as you walk in. I've given you my contact information in case you have any questions, but I'm also open to any questions you may have today.
Thank you, Vinod. Any questions? Okay.
How much instrumentation of your libraries and apps do you need to get this to work?
I'm sorry, could you say that one more time, please?
How much instrumentation is necessary to get this to work?
So our software runs on each node on your cluster. So it's a pretty easy install. And it collects all the information and shows it to you in an offline dashboard. So you can view it at any time. You can compare multiple runs of your job. And that part doesn't impact. The analysis of the software, of your data is done offline. So that doesn't put any load on your cluster.
Do I need to make any code changes?
No.
which one? Okay.
Hello, I saw you were doing, I guess, metrics for HDFS reads. Are you able to do metrics for other data stores like S3 and Google Cloud Storage and those kinds of things, or how does that work?
So we're integrated with Yarn. That's pretty easy to extend to anything else. We're looking at HDFS because that's the layer of software that Spark accesses typically when it's on a Yarn cluster. But yes, it should be easily extensible. Right now, we do HDFS, but we also do direct disk I/O as well.
Thank you.
Would you kindly describe a successful use case where this was an instrumental and it made a major impact on the business?
So I can give you two examples. I can't give you the names, but I'll give you the example. So in one case, we had a customer that's in healthcare. So they had this frequent problem where they had customers running their workloads in development and moving them to production, and that's when things kind of fell apart. One of the problems they had was my application is taking 1 gig, roughly 1 gig on all stages. In one particular stage, it just spikes through. And they basically used these multiple tools. They used Spark Web UI to get one part of the answer. They looked at event logs to get the other part of the answer. They looked at our software, our application, our products to get the time series. So they were doing what I showed you earlier, taking different pieces of the puzzle and making it together. What we did was to say, let's make that easy for you and let's integrate it so you can get that answer without having to look at multiple pieces. Another example is that goes with the cluster weather, where a customer had a run of an application that took 20 minutes or 20 to 40 minutes. I don't quite remember the exact time it took for the fast run. But all of a sudden, it took 4 hours. And they couldn't figure out what was going on. Why did the data change? What changed in it? And knowing the cluster weather basically said, oh, we know what was causing that delay. In their case, it was a disk I/O problem they had. Does that answer your question? Sure.
Anybody else? Okay.
One of the graphs that you showed the resource consumption by one of the apps, which was kind of blocking the other app, right? How did you resolve that issue actually? Because
how do you resolve the issue?
Yeah, because you are sharing the resource between different apps on the same host.
Yeah. So this would be more from this is information that the cluster operator gets, right?
Okay.
And so let's say that this your application in green had an SLA that it needed to meet. You could choose to put it on its own queue with its own resources and say, I'm going to give this special resource. I'm going to set this aside. Our other product lines also have the ability to do, it's called policy enforcer. So you can set a policy to say, hey, this application gets a guaranteed resource. And that way you know that you will meet your SLA. There are multiple, you can do it without our product too, but you can do it with other products that we have as well.
Just a follow-up question on that. If you have a dedicated resource, does that cost you extra?
That's why you would not want to have like dedicated queues. That's why we have products that kind of say, hey, we'll let you have your cake and eat it too. We'll set a policy. If nobody wants that resource, anybody can have at it, whoever needs it. But if the application that you have said needs this much resource, then we will guarantee that the other applications don't take it.
Thank you.
Thanks, Vinod. This is Chris from Pepperdata. Just a reminder, if you fill out these survey cards, 3 super quick questions, $200 Amazon gift card drawing. I'll be by the back with the little tiny questionnaire form in the box. And if you need to run out, you can fill it out and bring it to the booth later today.
Thanks, Chris.
Yeah, a few other questions.
There's another question over there, lady over there.
Okay, thank you.
So what is the overhead of running this tool on the existing application?
So we've done extensive performance benchmarking on our software. We are a performance company. We don't want to be impacting your performance. Typically, it is 1% of one core of your CPU. That's our overhead.
Okay, thanks.
Okay. Any other questions? Great. Okay, let's thank you, Vinod, for the great talk.
Thank you.